Rudolf Clausius' 1858 treatise on the moving force of heat and the laws of heat, which may be deduced therefrom, stands as a pivotal moment in the development of thermodynamics. Preceding this landmark work, the field was a nascent collection of experimental observations and fragmented theoretical insights. Sati Carnot's foundational work, Reflections on the Motive Power of Fire, published in 1824, had elegantly analysed the efficiency of heat engines, introducing the concept of a reversible Carnot cycle. However, Carnot's analysis relied on the then prevalent caloric theory, which posited heat as a conserved fluid. Clausius, building upon Carnot's insightful observations, but rejecting the caloric theory, revolutionized thermodynamics with his precise mathematical formulation. Central to Clausius, with 1858 paper, is his precise articulation of the second law of thermodynamics. He didn't merely restate earlier ideas, he meticulously reformulated them, grounding them in a robust mathematical framework that transcended the limitations of prior conceptualizations. He introduced the concept of entropy, though not using that term explicitly at this stage. Instead, he demonstrated an inequality, now recognized as a statement of the second law, governing the transformation of heat into work. This inequality is expressed as the integral, across a reversible cycle, of the ratio of an infinitesimal quantity of heat transferred to the absolute temperature at which the transfer occurs, being less than or equal to zero. This rigorous mathematical formulation provided a precise and testable statement of the irreversibility inherent in natural processes, a concept alluded to but not fully formalized in earlier works. The immediate impact of Clausius' work was profound. His articulation of the second law, expressed through his precise mathematical approach, provided a framework for understanding and analyzing the efficiency of heat engines with unprecedented accuracy. Engineers could now move beyond qualitative assessments and calculations based on flawed assumptions toward quantitative predictions informed by rigorous theory. Practical applications immediately followed, improving the design and efficiency of steam engines, then the mainstay of industrial power. His work provided the critical theoretical backbone for the burgeoning industrial revolution, enabling more sophisticated engineering designs that maximized energy extraction and minimized wasteful heat exchange. Subsequent developments built directly upon Clausius' foundation. William Thomson, later Lord Kelvin, independently formulated a mathematically equivalent statement of the second law, clarifying the concept of absolute zero. The collaboration and subsequent divergence between Clausius and Kelvin spurred further development of the field. Clausius' work provided a crucial stepping stone for the development of statistical mechanics, spearheaded by figures like Ludwig Boltzmann and James Clerk Maxwell. Boltzmann's formulation of the statistical interpretation of entropy, directly building upon Clausius' insights, connected the macroscopic laws of thermodynamics with the microscopic behavior of constituent particles, offering a deeper, more fundamental understanding of thermodynamic principles. Initially, Clausius' work wasn't universally understood or accepted. The concept of entropy, while implicitly present in his 1858 paper, required further clarification and refined mathematical articulation. Over time, however, the predictive power of Clausius' theory and its elegant mathematical framework won over skeptics. The experimental verification of his predictions and the success of its applications in engineering solidified its place as a cornerstone of thermodynamics. The initial resistance was overcome due to the undeniable success and explanatory power of his framework. The ensuing decades witnessed refinements, extensions, and elaborations upon his work, but the core principles he expounded in his 1858 paper remained fundamental axioms of the genesis of Clausius' 1858 paper lies inextricably in the preceding work of Sati Carnot. While Carnot's analysis was brilliant, it relied on the flawed caloric theory. Clausius explicitly acknowledged Carnot's contributions, but he radically departed from his predecessor by jettisoning a caloric model and replacing it with a superior, more precise mathematical treatment. Clausius' work is a direct response to Carnot's limitations, a sophisticated refinement of a powerful theory hampered by inaccurate assumptions. His achievement wasn't merely incremental, it represented a paradigm shift in the foundational understanding of heat and energy. Clausius' work directly influenced the subsequent research of many others. His mathematical formulations and precise statements of thermodynamic laws became essential tools for generations of physicists and engineers. His approach was adopted and extended by Gibbs in the development of chemical thermodynamics, providing a quantitative framework for understanding chemical reactions. His work also influenced the development of statistical mechanics, with Boltzmann and others building upon his ideas to create a statistical interpretation of entropy. The impact of his 1858 paper resonates throughout the physical sciences. Its influence felt far beyond the immediate realm of thermodynamics. In summary, Clausius on the moving force of heat and the laws of heat, which may be deduced therefrom, represents a transformative moment in the history of science. It wasn't merely a contribution to a field, it was a foundational restructuring of a field. His precise mathematical formulations, his rejection of outdated assumptions, and his profound insights into the nature of heat and energy revolutionized thermodynamics, setting the stage for countless subsequent developments in physics, engineering, and chemistry. The enduring legacy of this work underscores its profound and lasting significance. It serves as a compelling example of how a single work, meticulously crafted and filled with rigorous analysis, can profoundly shape the trajectory of an entire field of scientific inquiry, leaving an indelible mark on our understanding of the universe. The very elegance of his mathematical argument perhaps provides a subtle ironia concept so mathematically counterintuitive initially. It presented a notable challenge to even the most seasoned minds of the time.